Hi, and welcome to Dr. V's AP Chemistry podcast. Today we're talking about limiting reactants or limiting reagent problems. What I'd like to do in this webcast, I'd like to use picture models to illustrate these situations when we're using limiting reagent. It's very important that you understand it on a conceptual basis. I'd like you to have an easy way to identify these limiting reagent problems because it's really easy to overlook them. I'd like to show you one strategy out of several for solving limiting reagent problems. I'm only going to show you one, but I know of at least 3 others that are also perfectly okay. But there's only so much time. And we'll complete a practice problem that involves a limiting reagent situation. So let's say we have this reaction. A2 reacts with 4B to make 2AB2. And initially we had 4 molecules of A2, the little red circles, right? They're diatomic molecules, so we have to have all the atoms. And 8 atoms of B, all right, or the little blue triangles. And they're going to react together in this 1:4 ratio to make AB2 molecules. Great, so if we let them all react, all right, we're going to make 4 AB2 molecules if we put them all together. But it turns out we run out of the B atoms and we have A2 molecules, 2 of them, left over. So it's important that you understand this idea conceptually. I use up one reactant completely before the other one is exhausted. So in this case, all right, the B atoms are the limiting reagent. I ran out of B. I had leftover A2. And my theoretical yield was 4 molecules of AB2. On a particle level, the limiting reagent is fairly easy to figure out, to make sense of, and to figure out, what's going to be in excess and what's going to be consumed first and what your theoretical yield will be. However, when you're in the lab and you're trying to do these problems, it's not so easy to tell unless you do a bunch of stoichiometry calculations to figure that out. So I do want to point out that these really are stoichiometry problems. Keep your calculator handy, keep your periodic table handy. You're going to need them. All right. Because they are stoichiometry problems, make sure you start with a balanced equation. Depending on the situation, you may or may not be given one at the beginning. So check your formulas, make sure your polyatomic ions are correct, make sure your subscripts are correct, balance the equation. Make sure you know what you're solving for. They're often given to you as word problems, so you do need to read them carefully and make sure that you solve for something appropriate and pay attention to your units. So in terms of recognizing this situation, when do you have a limiting reagent situation? It's a lot, all right? The information given to you in the problem is going to include mass information for 2 or more reactants. So it's possible that you have a reaction with 3 or more reactants. If you're given information for more than one, it's a limiting reagent problem, all right? So if you've got mass, then, the grams over the molar mass will give you moles of that substance. Sometimes you're going to be given gas volumes, so you may need to use the ideal gas law to solve for moles of the gas. Sometimes it'll be a solution of known molarity, so you have to use the molarity formula, moles per liter, to find the moles of gas. You could actually have density information here as well. So there's all kinds of different variations we can do on these problems. All right, so one strategy for solving these problems, of course, you have a balanced equation, you know what you're solving for, is to solve for the desired product based on the mass or moles of each reactant that you were given. So you're assuming here that each reactant is reacting completely, all right, that is being all used up. How much product would you get in that situation? You're going to do multiple factor label problems, one for each reactant that you were given in order to figure this out. So I said 2 on the slide, but sometimes, very rarely, you would need to do more. All right, so you go and you do those stoichiometry calculations, and the one that gives you the lesser amount of product, that reactant is the limiting reactant, and the other one is left over. And the amount of product that you calculated that was smaller gives you the theoretical yield of that product. So let's do a practice problem. Solid iron 3 oxide, which is found in iron ore, can react with carbon monoxide gas in a blast furnace to form solid metallic iron and carbon dioxide gas. Okay, so here's our reaction. And then it goes on to say, if a 45.2 liter sample of the carbon monoxide gas at 1.35 atmospheres and 225 degrees Celsius is combined with 35.3 grams of iron 3 oxide, what's the theoretical yield of metallic iron? So we've got a lot going on in this problem. I've got 45.2 liters of carbon monoxide gas at a certain pressure and temperature that are told, and then I have 35 grams of the iron 3 oxide. So I've got the masses, or information related to masses, of two different reactants, both reactants in the problem. That's how I know this is a limiting reagent problem. So our first step is to write a balanced equation. So I've got just the description of the equation here. Iron 3 oxide reacting with carbon monoxide gas. So I do need to make sure my formulas are correct, and they are. And then I'm going to make solid metallic iron and carbon dioxide gas. This isn't balanced. This is just all the formulas of the reactants and products. So I do need to just make sure everything gets balanced. All right, so that's no problem. Put in all the coefficients. You can't change any formulas, of course. So that's our first step. We've got that balanced equation. And of course, if you need to pause something or repeat it, you're going to do that. All right. If we look at the original problem, we go all the way down to the bottom. I've highlighted in red. It says, what is the theoretical yield of metallic iron? That's what we're solving for. How many grams of metallic iron did we make? So I'm going to start with the carbon monoxide just because I'm going to. No particular reason. There's no reason why one has to be done before the other. I have a 45.2 liter sample of carbon monoxide at 1.35 atmospheres and 225 degrees Celsius. All right. I've got a volume and an atmosphere, a pressure and a temperature for the CO. I'm going to use the ideal gas law to find moles of CO. All right. I could find grams too, but moles will be sufficient. Otherwise, I'm just going around in circles. I can rearrange it to solve for just moles, PV over RT. I do need to remember to convert my temperature to Kelvin. My volume's already in liters, and so I need to make sure that when I go to select the value for the R constant, that it's in atmospheres and liters and Kelvin. So you do have to pay attention to your units, and you do need to pay attention to sig fig. So now I can substitute in all my values. All right. The pressure, the volume, the R constant in liters, atmospheres per mole per Kelvin, and the temperature in Kelvin. All right, I just added 273 to the Celsius temperature. I do that, I get a value of 1.49 moles of carbon monoxide. Great. Once I have this, it's pretty easy to calculate my yield based on just the carbon monoxide. I've got that balanced equation. All right, I know that 3 moles of carbon monoxide react to form every 2 moles of iron. So that's really my next step. Let's put that in the factor label, all right, so that the moles of CO cancel out for 2 moles of iron. And then I can multiply that by the molar mass of the iron. And that gives me a predicted mass, a theoretical product yield of 55.5 grams of iron. Fine. But I'm not done yet. I've only done this for the carbon monoxide. I need to do the same kind of process for the iron, based on the iron 3 oxide that we started with. You might recall we started with 35.3 grams of iron 3 oxide. That's what the original problem said. So we need to set up our factored label to solve for grams of iron based on this. All right, so how many grams of iron could I get if all 35.3 grams of Fe2O3 react? All right, so I need to divide by the molar mass of Fe2O3, right? And then I need to multiply by the appropriate mole ratio. And since I've got 2 moles of iron for every 1 mole of Fe2O3, I just set up my mole ratio accordingly. And then I need to multiply again by the molar mass of iron, which is 55.85 grams. So I've got my factor label all set up. All my units cancel out appropriately. And I'm going to get a value for the mass of iron that this would give me, which is 24.7 grams of iron. Great. So now I've done the hard work. You've done the heavy lifting at this point. Now what we need to do is compare the two answers that we got, because we did 2 calculations for the mass of iron that would be produced. Well, they're not the same. That's not surprising because we knew it was going to be a limiting reagent situation. All right. The one that is smaller, clearly 24.7 is smaller than 55.5 grams. All right. And since the 24.7 grams of iron is a smaller number, that means that's my theoretical yield of the iron, 24.7 grams. And that also means that the iron 3 oxide is the limiting reagent. That's what's going to be used up first. I'm not going to have any Fe2O3 left at the end of the reaction. And it also means that the carbon monoxide is in excess. There will be leftover carbon monoxide at the end of the problem. These are an important problem type that AP Chemistry students need to be very comfortable doing, no matter what information you're given about the reactants, whether it's, a certain volume of a liquid with a certain density, or you're given molarity and a certain volume of that solution, or just all masses. This is one approach you can use to successfully and quickly and reliably solve these problems.